record, and then I will upload this later today to Canvas. So I'll record the session, like I said. So everybody, we are actively recording right now. What I'm going to do is I have some documents here that I just wanted to show you, one of which is a review. So this is what the inside of your front cover will look like in the exam booklet. Very similar to this, you'll have some constants, some, symbols that are defined, so you don't have to memorize everything, if that makes sense. So you'll have some constants, you'll have some key equations that we did not cover, so you may not find use for these specific equations, but they're given usually. And you'll also have a simple periodic table like this. So as long as the main group numbers up top, what they represent, that the number below the elemental symbol is the atomic mass, the molar mass, um, you should be able to interpret any periodic table. All right, so let me stop share this because that's all I wanted to show you was just the front cover there. And then I have another review somewhere. Okay, hold on. I have to make sure it's up in the background so I can share it. Give me 1 second here, guys. Oh, okay, so you should be able to see this in just a moment. So you can disregard the little disclaimer at the top here. Um, don't skip any material that was not covered in our class. It's in your best interest to guess, even if it's a concept on the exam that we did not cover. Just at least use your best guess. But 90% of the material we have covered, we've reviewed, you will have seen practice problems for. And if there is anything that wasn't covered as a specific topic, you should be able to at least eliminate choices and make a good educated guess. So that's what I'm going to try to help you guys do here. Kind of recall some of the information that we introduced early in the semester, maybe talk about some shortcuts, some techniques. Let's see here. And I should be able to draw right on this document here. But please feel free to jump in if you do have any questions. So a question like number 1 here, we're asked to express this in scientific notation. So if you recall, when we have a number here, this is our standard notation. To get it into scientific notation, we have to get behind this first non-zero digit. Oh, it's moving the whole screen there. So I have to move my decimal place from in front of the zeros to behind that 4. So I have to move it 1, 2, 3, 4, 5, 6 hops until I get 4.3 if I rewrote my coefficient here. And then because it was, this is a little shaky, because we did 6 moves to the right, we're going to have 10 to the negative 6. All right. Not sure why it's moving the screen as well, but that's okay. Um, so answer choice C here would be our best option. Oh, I'm sorry. No, answer choice B. Sorry. We want that negative exponent to express this value in meters in scientific notation. All right. So I'll try to see if I can stop the screen from moving with me, but let's see what we have here. Our next question asks us to recall what the correct number of significant figures would be. So we're not doing any calculation. So all you have to do is look at the numbers, right? We don't have to figure out how many sig figs we should have at the end, but we can just look at A here, for example, and we know that any leading zeros, so these zeros here would not be significant, but these trailing zeros would be. So in this first, we would have 4 sig figs in this first number here. The second, same rule applies for the zero rules. Leading zeros, not significant. We don't have trailing zeros here, but I do have this sandwiched 0. So not only the 3 and the 2 are significant, we would have 3 sig figs here. So So far, we're looking for the correct number. Ooh. And we have 5, we have 2 listed, so we're incorrect so far. And then answer choice C, this does only have 3 sig figs. Those trailing zeros there without a decimal place, so I'll try to put a decimal place there. If that was placed in this number, I would have 6 sig figs. But since I do not have that decimal place there, this is the correct answer choice here. For number 2, it would be letter C, because we do have 3 sig figs, the 1, the 5, and the 6, but none of the zeros. So answer choice D would have 3 sig figs. Ooh. And then answer choice E, we have 5. All of those zeros would be significant. So the only correct notation there is answer choice C. Okay. We'll do a couple from each section. This packet or this practice test that I am using here is broken down into different topics, different sections. So I'll do a little bit from each for us. So this is again introducing conversions, conversion factors here. And what we see are kind of setups for calculations. And we're asked to find, let me see if I can get rid of that draw here, the correct number of sig figs at the end of our process here. So what I see in answer choice A is that I begin with 4 significant figures. So that's the maximum that you will ever end with. And you can see that we have 7, 100.1942. So that's way too many sig figs. So that's definitely not correct. Answer choice B here, we have 2 liters. That's only 1 sig fig. So the fact that I have 3 2.12 quarts in my answer, that would not be correct. Let's take a look at answer choice C here, and I'll explain why this is correct. So we begin with 4 significant figures. We can see that here, 24.95. If you recall conversion factors, so what I have, oh, right there in the middle, that 1 hour per 60 minutes, that will not affect my total number of sig figs at the end. So, ooh, let me see if I can annotate this way. So, oh, here we go. So what I see here is that I end with 4 sig figs, just like I began. So this would be the correct number of sig figs, because my conversion factor, this thing in the middle here that I'm circling a bunch of times, that will not affect my sig figs. So conversion factor does not affect sig figs. Sig figs. Okay, so that's good to note. So answer choice D, we see 3 sig figs here that we start with, but then over here, only the 3 and the 7. So there's only 2. So that's why answer choice D is incorrect. And then we have 3 sig figs here, 2 in my final answer for E. All right, so any questions so far? Do you guys remember sig figs? All right, I'll look for hands, I guess. Sorry, I can't see the chat while I'm sharing. So if you want to raise a hand, I'll stop. If not, my policy, I'll just keep moving. All right, let me move down here. I think we've covered kind of a wide variety of choices here in this first section. Oh, equivalent values. That's another good kind of topic to discuss. Oh, see, now when I annotate the other way, sorry guys, let me just share and reshare. That'll remove all those writing marks here. There we go. So these equivalent measurements here. So some of these involved, conversions as far as just noting the power of tens and prefixes. So number 4, I'll take a quick stop here. We want to know what's not equivalent here. So we have to do some conversion. So milligram to gram, right? We look at the units given in answer choice A here. So if I have 25 mg, to get this to grams here, I have to divide by 1,000. So you're expected to know these conversion factors between gram, milligram, kiloliter, liter. millisecond, second, centimeter to millimeter, deciliter to liter. So any of these units, I would know the powers of 10 between them, the prefix, what they mean. So in this case, a milligram is 1,000th of a gram. So if I divide by 1,000, I'm going to end up with 0.025 grams. Another shortcut is if I move 1, 2, 3 hops over here, place a decimal place. So you can do it in your head, you can do it on the calculator, but A looks good. That's an equivalent value. To go from liters to kiloliters, that's 1,000 times. So I would have to divide my 183 to get to kiloliter units, and that would be what I end up with here, 0.183. Next, I have 150 milliseconds. So this is also another unit of a 1,000 in difference between seconds and milliseconds here. So if I took 150, divide that by 1,000, I'm going to get my 0.150 seconds. So that one checks out. Uh, D here, D is a little suspicious because I'm going from a larger unit to a smaller unit. So I would expect my coefficient, my numeric value here to enlarge, to get larger. So I would actually have 840 millimeters if I did this conversion properly, because I would multiply by 10 here. So D is the only incorrect or not equivalent value given. I'll tell you deciliter here, that's 10, or 1/10 rather. So 1 deciliter is 1/10 of a liter. So if we did 24, we'll start over, divided by 10 here, that's where we get 2.4 liters equals 24 deciliters. So that's also a true statement. So review not only your conversion factors between all the SI units, right? So gram to milligram, the powers of 10. So know that there's like 1,000 difference between milligrams, let's say, to grams. And as we go through, I'll pick out any other units of interest. All right, so I'm gonna stop share, reshare. We'll move to the next section. I don't see anybody with any questions yet. All right, and remember, I know I'm moving quick. That's just so I can get through a lot as quick as possible. But you can always go back and replay. Hmm. Oh, I do want to remind you guys to make sure that your units cancel. So say you have a problem like 5, this just tells us what do we need to set up, or asks us rather, what do we need to set up here? So we want to go from centimeters to feet. So this is just very generic rather. So we don't even know how many centimeters we have. So you could just plug in a value if you want, but we start with centimeters, and then we see the conversion factor here that this would tell us that 1 centimeter equals 2.54 inches. So this is set up incorrectly, this conversion factor. So A is not a good choice because of that. But if I go to B here, I can see that I have the correct relationship with my conversion factor, but my units don't cancel. So centimeters and inches would not cancel out. So B is not correct because of the orientation, the way that my conversion factor is plugged in. Then if I go to answer choice C here, we can see this looks a little more promising. Centimeters will cancel with centimeters. Inches now, 1 inch would cancel with my 12 inches per foot here. So answer choice C would be a good one for this type of question. So don't forget to make sure your units cancel and that your conversion factors are oriented in the correct way. And then usually problems don't require lengthy calculation. They'll just require setup, and then you usually can eliminate answer choices, but calculations should be short and quick. So something like 6 here. Uh, I promise I'll get to the next section in 1 second, but I keep seeing stuff that's good here that we should look at. So this is medically related. So you could be given orders for 0.125 grams of ampicillin to be delivered. This is our target, right? This is the value that we're given. So I'm going to start with that. 0.125 grams. And then this value here, if we have this liquid suspension, so that means that we have some ampicillin floating around in some kind of liquid, water, or something else. So we have this conversion factor here, right? That's given. So we have that for every 5 milliliters, it kind of cuts off on the other line here, but for every 5 milliliters, I can deliver 250 milligrams. So if I only need, this is my target, this 0.125 grams, I can take that and then divide by this value in grams, this 0.250 grams, right? I'm going to convert my conversion factor to be in the same unit so that it will cancel. And then I just need to flip my conversion factor so that my units do cancel. So now that I'm in grams here, I'm going to put my 250 milligrams as 0.250 grams down here. And then I'm going to multiply by milliliters. And I see that that's what I'm looking for here. How many milliliters do I need to dispense or should be given to the patient here? So I want my units to cancel, grams do. I end up with milliliters. So I would divide 0.125 by 0.25, and then you would see that that's a half. So 1/2 times 5 gives me answer choice C here. So 2.5 milliliters would be perfect for this patient. All right. Oh, density, just since we're here, and this is really quick, density is mass over volume. I have mass. I have my starting volume, so my volume initial. I have my final volume. I know that my volume displacement, my change in volume is what I should use here. So I would do 77 minus 20, or I'm sorry, minus 50 rather. And I would see that my volume would be 27 milliliters, right? 77 is my final minus my initial. That gives me 27 milliliters of volume for this gold nugget, and then it weighed 521 grams. So here, I'll put it all together over here. 521 divided by 27. If you do that math in your calculator, you'll get about 19.3 grams per milliliter, or exactly that. So don't forget the density equation, some simple equations like that that we learned early on may not be given in the front cover of the booklet because they're, like I said, they're pretty simple, easy to remember. They'll give you some harder stuff. Um, so you can devote your brain to more deductive reasoning and memorization of conversion factors. Um, all right, so we'll come back to some of this stuff if we have time, but let's move to this next section here that kind of encapsulates energy and matter, the physical or chemical changes that may relate to those topics. So energy and matter, again, is going to be our focus here. Um, and we're given this information. We have a solid that's converted directly to a gas. So you'll have scrap paper. I recommend you write down, just pull out the information, either if it's numeric data or in this case, a phase change. So we have solid to gas. If you recall, I mentioned dry ice, so CO2 solid at normal atmospheric pressure and room temperature, CO2 does not exist as a liquid. It has no liquid phase. So this is an example of what we call sublimation. So when we go directly from solid to gas, we're subliming. If we do the opposite, if we go directly from gas to solid, if you remember, like water vapor on a very cold night can turn into ice crystals on a blade of grass. That would be deposition. So I would know, the 6 main phase changes: solid to liquid, solid to gas, gas to liquid, gas to solid, liquid to gas, all those in between. Mhm. So that was 23, answer choice E. Uh, 24 here. This is more like a definition of a gas. Sometimes some questions will be more like definitions. So in this case, we're asked about a gas and the distance between the particles. So the gas particles in, the gas that we're talking about. So they're not close, right? Because that's a solid, right? When particles are really close, but a gas, they're far apart. So there's a great distance between them. So the distance between them is very large relative to the size of the molecules. So if we read through, we would see that's the best description of a gas. Um, Fixed relative to the size of the molecules, no, because the gas expands. Close relative to the size of molecules, no. There's a lot more space between the molecule than the size of the molecule. And small relative to the size of the molecules, no. So the molecules are not bigger than the space between them. That would be what D is saying. So answer choice D is wrong because of that. So we'll look for some definitions, look for some ways to quickly eliminate answer choices. Helium, well, let's think about this. What is helium? Again, this is like a definition. So I'll draw helium. My helium atom, it's a noble gas. So it's not diatomic. So it's not a compound. So I won't get confused and think that it's a compound or a molecule. A heterogeneous mixture. No, because we're just told that we have helium here. So don't try to add things in. Don't try to think, where's the helium? What's around it? We're just focusing on the helium. Is it an element? Yes, it's definitely an element. Is it a homogeneous mixture? Well, no, because we're just talking about helium and we need two or more things. It's not an electron. No. All right. So don't try to think more details. Don't try to add outside stuff to beyond what you're given. That will confuse you and make you think longer than you need to. All right, let me stop share here so I can get rid of all this writing. And then I'll take a deep breath. Any questions yet? Okay. All right. So we'll keep moving. Maybe I'll go to the next section in a moment, because we're already 25 minutes in. All right. All right, let's see. What is the next section here talk about? Air we know is a homogeneous mixture, right? Because all those different air particles are air molecules. So I'll just say homogeneous mixture so I don't have to erase. Let's see, which is a chemical change. So do you guys remember chemical, physical changes, chemical, physical properties? So what's the key question we ask ourselves? Do I have the same stuff as what I started with, right? So for a chemical change, my answer should be no. No, I have something different, right? So we're asked specifically here about a chemical change. So if I were to cut a rope, no, I just have two pieces of rope. So nothing chemically happened there. Bending a steel rod. So well, instead of breaking something, now I'm just deforming it, I'm bending it. So no, no chemical change there. Making a snowman. Well, we're just changing the shape of the snow. It's wonderful. Burning sugar. Well, now I don't have my white, crystalline looking sugar. I might have caramel. I have something more blackened, brownish, kind of gooey. So that definitely would be a change, in appearance and in structure. So burning sugar is a chemical change. Melting, that's also a physical change. So remember, physical versus chemical changes. And you ask yourself, do I have the same stuff? Right? Same stuff. That's the main question. So what's a physical change down here now? The opposite, if you will, of a chemical change, right? We keep the same stuff now, but we might have a phase change. That's the most common physical change that we're going to see. So dry ice subliming. So we had dry ice, we had CO2 that was solid, and then during this phase change, My CO2 is now a gas. It has sublimed. Baking a cake, that's going to involve some chemical changes, right? So we'll cross that out. Fermenting grapes. Well, I have, alcohol, and before I had grape juice. So that's out. Digesting a meal. Oh, if you can see that one down there. That also involves some stomach acid, some type of chemical process. So um, let's see here. And then there should be one more option here. Tomato ripening. Yeah. So all of these indicate some type of chemical change, some chemical process, except for our dry ice subliming. So again, think about, do you have a phase change? Do we have the same stuff as we start with when we're talking about physical versus chemical changes? And then if we were asked about physical versus chemical properties, you would have to change your substance to observe a chemical property. So just keep that in mind. So boiling point, melting point, things like that, we don't change our substance to observe these things. We just have a phase change. Let's see here. But if we want to know if something reacts with an acid, we have to react it with an acid and then it changes. Okay. Um, oh, here we go. Here's a calorimetry problem, number 29 here. So you may be asked to calculate the amount of energy that you need to raise the temperature. So this was a calorimetry type of problem. Oh, where's my writing? Uh, sorry, guys, I lost my writing. Here we go. Um, nope. Sorry. I'm on the wrong screen now. Sorry about that. Here we go. Okay. Doesn't want to let me write for some reason. There we go. There we go. All right. So, let me get started here. So we have, Q. If you recall, that's our heat. When we're dealing with these calorimetry problems that we can calculate, we need mass, we need a specific heat capacity, and then we need a change in temperature. So if you read through this question, we're asked how many calories, not joules, right? We worked mainly in joules and kilojoules, but we can do the same type of calculation just using a different unit of energy. That's the only difference here, is that we're measuring this energy, this heat, in calories versus joules or kilojoules, which we've used in the past. So same equation. We need a mass here, so that's my M. I need my delta T. So if I look at my from, so this is my initial temperature here, 25 degrees Celsius. 2 will be my final temperature, right? My TF. And then my delta T will be equal to T final minus T initial. So we're going to have 175 minus 25. So my delta T here is 150 degrees Celsius. And I'm going to write down below here because I crowded myself. I ran out of space. So we have our Q calculation is going to be my mass in grams, my C, which is given right here. Notice the unit's almost the same, joules per gram degree Celsius or Kelvin, but now we're in calories. So we're going to plug this in the same way that we would a different specific heat capacity, right? That was given in joules or kilojoules. But now I have calories and my denominator is still going to be grams per degree Celsius. So once we plug in our delta T on the end here, this 150, we can see that my C cancels, my G cancels. I'm left with a unit of calorie. So I have 150 times 150 times 0.3. And if we plug all this in, we should get 693 calories. All right, so no calorimetry, this type of process where when we measure a temperature change, if we're given a mass and a specific heat capacity, that value for C that I plugged in, right, the specific heat of gold, then you can solve this type of problem. All right, so I'm gonna move to the next section here. So we looked at energy and matter. Section 3, atoms and elements. Okay, so this should be hopefully mostly review because we've been nonstop talking about atoms and elements the whole semester here. So you should know how to differentiate between metals and nonmetals, know their position on the periodic table. So what's a metal? Nitrogen, nonmetal, fluorine, nonmetal, argon, nonmetal, specifically noble gas, strontium. Yes, that's a metal. Phosphorus, also a nonmetal. If you forget, there's like that staircase, everything above is going to be a non-metal up in the right, and then metals are below. On the periodic table, that staircase that separates them, that metalloid region. But you can just know in general, upper right hand, non-metals, carbon, nitrogen, oxygen, metals in the middle, and groups 1 and 2. And all right, let me just we'll erase here. Nope, sorry, stop share is easier. Okay. All right. So, know the noble gases. So argon is number 40. That's in group 8. So anybody in group 8, group 8A, the main group 8A will be a noble gas. We're looking for properties similar to magnesium. So I'm going to look in the same group with magnesium, right? So magnesium here is in main group 2. So strontium is also in group 2, right? Strontium, we know it becomes a +2 ion. All these things are good to know about group 2 metals. They're alkaline earth metals. Okay. And sorry if I'm giving you whiplash. It's just way quicker and easier than me erasing to go in and out here of the share. Subatomic particles. All right, so what are those? Those are electrons, neutrons, protons. We talked about these very early on. Proton is positive, has a mass of 1 atomic mass unit. So that's a true statement, right? So 42 A would be a good answer. Electrons are negative, but they don't weigh quite as much as a proton. A neutron does. A neutron is also 1 AMU, but it has no charge. Mass is negligible with an electron. So you might see descriptions of these subatomic particles, know the main differences. We should also know how to calculate mass number. So mass number is going to be, if we have our elemental symbol, it's the top number here, our A number. Oh, that's nothing over here. And then we have down below our Z number. So if you recall up top, the mass number is going to be protons and neutrons, right? The heavier particles, the ones that weigh 1 AMU each approximately. So we have protons and neutrons contributing to our mass number. Down here, our Z number, that's just protons. So if we were to look for the best answer for number 43, we have the number of protons plus neutrons, right? So that's our mass number. All right, correct symbol for an isotope of potassium here. So, so if you have your periodic table handy, or day of the exam, you can look in your front booklet cover. We would notice that potassium is element number 19. It's in group 1A. So we would have here, oh, where's my notation again? Potassium with 22 neutrons. So we know that 19 is going to be the Z number, right? The number of protons, right? Because it's the elemental or atomic number rather on the periodic table. So we found that on the periodic table. 22 neutrons. Now this is where I add, oh, sorry, not 20, 22 to 19, and I'm going to get 41. That will go up top. That's my mass number. So it looks like answer choice A would be the correct symbol, the correct nuclide symbol for our potassium isotope. Okay. All right. So I'll come back here for a second. Anybody with any questions? All right, I'll end maybe a few minutes before 11. That way I can stop record if you do have questions that you want to ask verbally. Let's keep moving though, because we have 20 minutes or so left. I'll keep powering through here. All right, so let's so we know what neutrons, protons, electrons are. Um how about something like 47? This was early on as well when we looked at the average atomic mass. So what's given on the periodic table, if you recall, is actually different isotopes of the specific element, and those masses of each isotope are multiplied by what we call their percent abundance, or how prevalent each of these isotopes are. So chlorine, we're told here, has two different naturally occurring isotopes. So the 35.0 AMU isotope is present about 75.8% of the time. So if I wanted to find the average atomic mass, I'm going to convert that percent to a decimal, plug that in here, multiply by my mass of that isotope, which was 35. And then, so this is my first isotope. Over here, we'll list our details of our second isotope. This is now chlorine 37 isotope. It has 37.0 AMU atomic mass. Then we have that makes up 0.243, 24.3% of the time. So we would multiply these two factors together, add them together, and we would find answer choice D here would be the average atomic mass to 3 sig figs. Your periodic table might have more digits than that, like mine has 35.453. Right, so just to be safe, you could do the calculation and make sure, or you can check on your periodic table and see what if you can determine which is the closest, the correct answer. But if you did the math, you would get the right answer no matter what. All right, so 48 is similar to this, but um, I'm gonna do some other types of problems. I mentioned earlier that I think maybe before I started recording that I will try to post this later today along with the video link. Oh, how do we know how many electrons are in the outer energy level? Well, that's asking us specifically about valence electrons, right? The outer energy level means valence electrons. So if we're asked about neutral, that means we don't have to add or subtract any electrons, what we would guess based on the group number. So borons in group number 3. So boron would have 3 valence electrons. So answer choice B here for number 49. So in general, anytime you're asked about the outer energy level, number of electrons, that is, code name for valence electrons. And then all you have to do is look at the main group number. You will not be given any transition elements without other information. So you won't have to guess the number of valence electrons for any transition elements. So know the main group number. So the main number, that gives you the valence electrons. Um, Electron configuration. We looked a little bit at this. So potassium. So we would go to our periodic table, and I'm actually going to go there for a second here because it's easier than talking about it uh, than just showing you. So let me go back to our cover of our booklet here, and there we go. All right, so if I wanted to do electron configuration, I use the periodic table to help me. I don't have to, memorize, everything per se. If I know that over here I have s orbitals, over here I have my p orbitals. We're only going to potassium, right? So we won't need the d orbitals, but we know they're there if we did need them. So we start off filling our lowest energy, so 1s2. So that gives me 1s1, 1s2 with helium. Then I go down to period 2, 3, 4, right? So period 2 starts 2s2, right? So now I'm through beryllium. Then I go over here, 1, 2, 3, 4, 5, 6, all the way through neon. Still in row 2, so I'm now in 2p, and I fill that through to 6. All right, so I'm up to 10 electrons. I need to get to 19. Let's keep going. Now we're in period 3, so I'm in 3s2. That knocks out up to magnesium. And then I'm in 3p, 1, 2, 3, 4, 5, 6. All right, 3p6 gets me through to argon and then potassium. I'm going to end, let's squeeze it in here, 4s1. So I would end with 4s1. And that makes sense, right? I'm in the fourth period, the fourth row. I'm in group 1 territory here. So potassium. I'm going to go back here to my answer choices. And we can quickly eliminate some answer choices that do not end in that 4s1, and then choose one that does. So a hint for, oh, let's come back here, for some time saving would be maybe not do the full electron configuration. Oh, why won't it let me share? There we go. Don't do the full electron configuration if you don't have to. Just look at the last orbital that's filled. That's kind of like a shortcut here. So, whoop, sorry guys, not letting me annotate again. All right, so I'll just talk about it here. So answer choices D and E. Those are the only two, here we go, that end in 4s1. So I have to make some other decisions here, but I know I can right away eliminate A, B, and C, right? They do not end in the right orbital. They don't even go up to 4. So now between D and E, I'll just make sure that we filled them properly. Let's see what's wrong here. So I see that 3p only has 5 electrons. When I know that I need to fill it with 6 before moving to the 4s. So I'm going to eliminate answer choice E as well. And then for number 50, we'll go with D here. All right, so electron configurations, Lewis dot structures. Carbon is in group 4. It will have 4 dots around it. Remember, you can think about like an imaginary box. So we would fill a dot on each side of our imaginary box, carbons in group number 4. So that's where I found the number of dots to put around my box. Say I had nitrogen, that's in group 5, so I would do 4 dots out of the 5, one on each side, and then I would go back and pair my one of my 5 dots. All right, so no Lewis dot structures, no electron configuration from this section. And, ooh, all right, I'm talking too much. Let me keep moving here. How about this next section? Nuclear chemistry. Okay, we just looked at this, and you have the nuclear lab worksheet and everything that you can take a look at as well. um, Radioactive isotopes. We're looking for just the nuclear symbol, a nuclide. So it's the same way that we would have done our mass number, right, our AZX notation. It's the same thing as in the previous section, but now we're talking about radioactive isotopes. So copper, right, we're told, so we know we have the same elemental symbol for all of these. So that won't help us eliminate answer choices, but we're told the mass number is 60. So if I don't see a 60 up top, I'm going to eliminate B, C, and E. So now I'm between A and D. So this is where I have to figure out my atomic number, my Z number, down here. So copper is on the periodic table, it's number 29. So I'm going to say answer choice A is the best, right, answer here. So my elemental symbol Cu. Sometimes they'll try to trick you with the wrong elemental symbol, maybe CO, but that's cobalt. The mass number is 60, that's up top, and then the number of protons, the atomic number is down here. So helium, this symbol here, that's an alpha particle. That's really memorization. Gamma symbol, gamma particle, looks like this. It has no mass, no charge. Remember up top, same way, we have mass number up top here. The only difference with these nuclear particles is that we commonly call this the charge number here, or this is how we account for charge. So, but we know this is the positive, right, number of protons here. So I have my alpha particle, right, a alpha. Then I have gamma ray here. And then my beta particle that you see as answer choice D here, that would imply an electron, which we know has no mass and a -1 charge. So beta. All right, so I would know just those three nuclear particles, how they're abbreviated, how they're represented. Um, and then we'll look at some of those nuclear equations. There's some easy math that we can do. If you recall, we just have to account for the mass up top and then the charge on the bottom when we look at these nuclear reactions. So there's our gamma, or I'm sorry, our electron, our beta particle for number 60 is D. Okay, and then here's that math that I'm talking about with the charge and the mass number. So let's look at these two examples here in full. Oh, okay, there we go. I can write. So I see here in problem 61 a nuclear reaction. And I know that it's a nuclear reaction, well, one, because I'm told that. So I can automatically recall that I need to retain both mass. So I need to kind of set up an equation here. So my mass on my reactant side, boron, has a mass of 10. This alpha particle, this helium nucleus here that I have has a mass of 4. And then on my product side, I see that I have nitrogen, which is a mass of 13, plus some unknown mass, right? So this is unknown here, both the mass and the charge. All right, so I can solve for this x. So my mass number must be 14 equals 13 plus x. So my x must be 1. Okay, so I know that I have something with a mass of 1, right? If I filled in my top box here. And then I'm going to do, this math on the bottom here to conserve charge. So I have 5 protons with boron. I have 2 protons in my alpha particle. That gives me 7. And then over here, my nitrogen already has 7. So that means that I have an uncharged or 0, right? X must be equal to 0. So that implies an uncharged particle. So something that has a mass of 1, a charge of 0 would be a neutron. All right, so neutron has mass but no charge. A positron has a +1 charge but no mass. So this is commonly abbreviated like as a positive electron, this positron. So again, it's the same mass as an electron, but an opposite charge. We know our alpha particle has a mass of 4, charge of 2. It's also a helium nucleus. Beta particle, remember that's our electron and abbreviate it like B. All right, so let's take a look at 62 here. Let me stop share for a second. So there's like 3 times this many problems in this packet that I'm going to upload. So you can look through, feel free to ask me questions about anything after today. But just note that I'm moving fast so we can try to get a view of as much as possible. All right, so 61 here. Oh, I'm sorry, 62. We just did 61. So 62. Uh, oh, doesn't let me move when I'm in draw mode, and I can't get out of draw mode now. All right, hold on. Hold on. Ah. All right, so I'm just gonna walk us through this number 62 without moving just to save time. All right, so I have my mass number for tungsten here, W, is 159. There's no other reactants. So 159, I'm going to set equal to my hafnium here, my 155 plus some particle, right? We want to know what particle is released again. So what's this blank here? So 154 equals 155 plus X, so I know that my X must equal 4. Looks like we're going to have an alpha particle, right? I have 74 on the bottom, and that's going to equal 72 plus X. So down here, my X is 2. Remember, 4 mass number, 2 protons gives us helium, which is an alpha particle. All right. Let me pause for a second here. Oh, okay. All right, so I'll just walk you guys through real quick before I do a stop share or a stop record. What else is contained here? All right, besides our nuclear chemistry section, if we keep moving along, we'll see some compounds and their bonds. So this has to do with ion formation, ionic bonding, covalent bonding, polarity, how to correctly name ionic compounds. So this is where we crisscross our charges here. Something like this iron sulfate. I know that this must be iron 3 sulfate because of that 3 subscript next to the SO4 if I uncrossed my charges. And then sulfate is always a -2. The diatomic, so that's just have no fear, right? So hydrogen, oxygen, nitrogen, iodine, carbon is not diatomic. Know how to make the Lewis dot structures. Remember, valence electrons start forming bonds. What other sections do we have here? So the molecular geometry stuff is in this section. And then chapter 6, or this next section, deals with different reaction types, quantities. So how many moles do you need to react with how many moles of substance? Just in general, number 94, for example, this is a decomposition reaction. So I would know double displacement, single displacement, decomposition. Combination is when you have two things that become one versus decomp here, where we have one thing that becomes two. Redox reactions, we're looking for a change in oxidation number. So a quick look at answer choice C here. I see that both nitrogen and oxygen are 0 oxidation state. So I know that oxygen in a compound rather, right, would turn into a -2, so would become reduced. And nitrogen in this neutral NO, answer choice C here, would have to become positive. So look for shortcuts like that where you see something where you know its oxidation state has changed. Um, so when we're looking for redox reactions, um, know, Avogadro's number, how that relates between grams to moles, and then number of molecules. So for this problem here, we want to know how many molecules of H2O and 75 grams. I would convert to moles first. So 75 divided by like 18, right? 16 for oxygen, 2 for the hydrogens, will give me moles. And then I would multiply by Avogadro's number. 6.02 to the 23rd. So don't forget to, again, align your units, make sure things cancel. We saw some problems like this, like 102, setting up conversion factors. All right, and then there's more and more here. Finally, we get to solutions and everything that we looked at towards the end of the semester. So you guys have an idea here. Let me stop share. I'll post this. It'll have the answer key. I'm going to stop recording right now. Maybe.